कैसे हो मेरे पढ़ाकू? बढ़िया, पढ़ाई कर रहे हो? गुड. Last time we have obtained the formula of torque acting on magnetic dipole placed in uniform magnetic field. This is uniform magnetic field B vector. When magnetic dipole is placed in uniform magnetic field, this is north pole, this is south pole of the magnetic needle. What will be the direction of magnetic moment? Magnetic moment is from south to north, correct? So this is the direction of magnetic moment, which makes an angle theta with x-axis. This magnetic moment makes an angle theta with magnetic field. When this magnetic dipole is kept at an angle theta, at the time torque acting on this dipole is mb sin theta. Torque acting on this dipole, that is mb sin theta. Now if I want to displace this dipole by small angle d theta, if I want to displace this dipole by small angle d theta, then some amount of work is required to be done. Then work done against this external magnetic field, that is nothing but integration of tau d theta. Yes or no? Integration tau d theta. Tau, that is torque, and d theta, that is angular displacement. What is torque acting on this dipole? That is mb sin theta, and this is integration with respect to theta. If I want to rotate this dipole from some angle theta 1 to another angle theta 2, then work done W is equal to mb integration theta 1 to theta 2 sin theta d theta. Therefore work done W is equal to mb, what is the integration sin theta? That is minus cos theta, theta 1 to theta 2, integration of sin theta, that is minus cos theta, is equal to minus mb, first limit cos theta 2 minus cos theta 1. Therefore work done W is equal to mb cos theta 1 minus cos theta 2. So this is the formula of work done in rotating this dipole from angle theta 1 to theta 2. Theta 1, that is initial angle, and theta 2, that is final angle. Same formula we have studied in chapter number 2. याद है? When electric dipole is placed in external electric field, at that time work done in rotating electric dipole from theta 1 to theta 2 is Pe cos theta 1 minus cos theta 2. Instead of magnetic moment, dipole moment P. Instead of magnetic field, electric field E. Pe cos theta 1 minus cos theta 2. But we know that whatever work is done by external force, that is stored in the form of potential energy. So work done by external force is nothing but change in potential energy. So delta U is equal to mb cos theta 2 mb cos theta 1 minus cos theta 2. This is change in potential energy. Change in potential energy means U theta 2 minus U theta 1 is equal to mb cos theta 1 minus cos theta 2. initially if I take this magnetic dipole perpendicular to magnetic field, then this theta1 can be taken as 90 degree. If initial position of magnetic dipole is perpendicular to the magnetic field, it means if magnetic moment is perpendicular to the magnetic field, then theta1 is equal to 90 degree. Then at this 90 degree angle, if I take potential energy 0, potential energy at this position if I take 0, then potential energy at theta 2 is equal to mb cos theta 1 cos 90 minus cos theta 2, correct? So the formula of potential energy U theta 2 is equal to mb cos 90, that is 0, minus cos theta 2. So formula of potential energy at some angle theta 2 is equal to minus mb cos theta 2. If I take theta 2 is equal to theta, then potential energy at any angle theta is equal to minus mb cos theta. Therefore, this potential energy can be written as U theta is equal to minus m vector dot b vector. This is the formula of potential energy. U theta is equal to minus m vector dot b vector. Same thing we have obtained in chapter number 2. Potential energy, electric potential energy is nothing but minus p vector dot e vector. What is p vector? That is electric dipole moment. What is e vector? That is electric field. तो सेम थिंग हमने ऑब्टेन की थी चैप्टर नंबर 2 में फॉर इलेक्ट्रिक डाइपोल प्लेस्ड इन यूनिफॉर्म इलेक्ट्रिक फील्ड. बट हियर इन दिस केस पोटेंशियल एनर्जी ऑफ मैग्नेटिक डाइपोल is minus m vector dot b vector. So there is analogy between electric dipole and magnetic dipole. So this way we can obtain the formula of potential energy of magnetic dipole placed in uniform magnetic field. टॉर्क मिल चुका है, पोटेंशियल एनर्जी मिल चुकी है. नाउ आई विल ऑब्टेन द फॉर्मूला ऑफ टाइम पीरियड. नाउ आई वांट टू ऑब्टेन द फॉर्मूला ऑफ टाइम पीरियड for the oscillation of magnetic needle placed in uniform magnetic field. This is uniform magnetic field B vector. Now if magnetic needle, this is magnetic needle which is placed at an angle theta with magnetic field. So this is the direction of m vector. M vector is in this direction. Now when magnetic needle is placed in external magnetic field at an angle theta, at that time torque acting on this magnetic dipole, that is mb sin theta, torque tau is equal to mb sin theta. When we rotate this magnetic dipole at some angle theta, at that time torque provided is mb sin theta. Now if this magnetic needle is free to rotate in this magnetic field, if I leave this magnetic dipole in this situation, then what will happen? Due to this external magnetic field, it will try to align in the direction of magnetic field. This is magnetic needle, okay, which makes an angle theta. At this angle theta, torque acting on this magnetic needle is mb sin theta. But now if I leave this magnetic needle from this position, then what will happen? This magnetic field will exert some restoring torque on it. कुछ restoring torque लगाएगी, जिसकी वजह से क्या होगा? This magnetic needle will try to align in the direction of magnetic field, and restoring torque acting on this magnetic dipole that is minus mb sin theta. Torque applied, that is mb sin theta. Due to this external magnetic field, some restoring torque will act on it, and due to that, this dipole will try to align in the direction of magnetic field. So restoring torque, that is minus mb sin theta. If I take this theta to be very small, if theta, that is very small angle, if we displace this dipole by very small angle theta, then this sin theta can be written as theta. Yes or no? When angle is very small, at that time sin theta can be taken as theta, because what is the value of sin? 0, that is 0. So when angles are very small, at that time sin theta can be taken as theta. So instead of this sin theta, now I can write restoring torque is equal to minus mb theta. क्या ठीक? So restoring torque is equal to minus mb theta. M, that is magnetic moment of the dipole. B, that is uniform magnetic field. It means M, that is fixed, B, that is fixed. Therefore we can say that this torque is directly proportional to minus theta. Yes or no? This torque is directly proportional to minus theta. याद हो तो हम पढ़े हैं ये चीज़, when f is directly proportional to minus x, at that time it will execute simple harmonic motion. Yes or no? Simple harmonic motion. Here torque is directly proportional to minus theta. Now here, instead of force, what we have? Torque. Instead of linear displacement, what we have? Angular displacement. Therefore this needle will perform angular simple harmonic motion. This needle will perform angular simple harmonic motion, because torque tau is directly proportional to minus theta. Now from this equation, restoring torque tau is equal to minus mb theta. This is restoring torque. Okay, restoring torque is equal to minus mb theta. But we know the relation between torque and angular acceleration. What is the relation between torque and angular acceleration? That is torque tau is equal to I alpha. Yes or no? Torque tau is equal to I alpha. Instead of I am writing IM, क्योंकि अगर I लिखूंगा तो तुम लोग इलेक्ट्रिक करंट समझ लोगे. This is not electric current, this is moment of inertia. What is this? Moment of inertia. IM alpha is equal to minus mb theta. Correct? What is the formula of angular acceleration? That is nothing but, that is the second derivative of angular displacement with respect to time. Angular acceleration is nothing but second derivative of angular displacement with respect to time is equal to minus mb theta. Therefore d square theta by dt square is equal to minus mb by I into theta. d square theta by dt square is equal to minus mb by im. ये mm कट मत कर देना. This is moment of inertia, minus mb by im into theta. Now this equation is same as the equation of simple harmonic motion. What is the equation of simple harmonic motion? That is d2x by dt square plus omega square x is equal to 0. याद है? d2x by dt square plus omega square x is equal to 0. This equation we have studied in standard 11. Simple harmonic motion में ये equation पढ़े थे. So this is nothing but d2 theta by dt square is equal to minus mb by im into theta. This equation can be written as d square x by dt square is equal to minus omega square x. Correct? This is the equation of simple harmonic motion. This is the equation of angular simple harmonic motion. So here comparing both the sides, x is equal to theta, x is equal to theta, omega square is equal to, from equation 1 and 2, omega square is equal to mb by im, where im, that is moment of inertia, m that is magnetic moment, and b that is magnetic field. Therefore omega is equal to under root mb by im. Now we know the formula of omega. Omega is equal to 2 pi f. Therefore 2 pi f is equal to under root mb by im. Therefore formula of frequency f is equal to 1 upon 2 pi under root mb by im. This is the formula of frequency. Frequency of oscillation, that is 1 upon 2 pi under root mb by im. But we are interested in the formula of time period. Time period is reciprocal of frequency. T is equal to 1 by f. Therefore time period t is equal to reciprocal of this, that is 2 pi under root I by mb. Im, that is moment of inertia. You can take I also. 2 pi under root I by mb. So formula of time period, that is 2 pi under root I by mb. This is the formula of time period of oscillation of magnetic needle placed in uniform magnetic field. Now what happens when this magnetic needle oscillate in this magnetic field? क्या होता है? Here when this magnetic needle is kept at some angle theta, and if it is free to rotate in this magnetic field, if we leave it in this position, and after that if it is free to move, then what will happen? This magnetic field will exert restoring torque on it. Due to restoring torque, this magnetic needle will move in this direction. Because at the time some work is done on this magnetic needle, when some work is done on this magnetic needle, then its kinetic energy will increase. Due to increase in rotational kinetic energy, magnetic needle will align in the direction of magnetic field. At the time its kinetic energy will be maximum, and if it has maximum kinetic energy, then what will happen? It will rotate further and it will move in this direction. It means when needle is kept like this in external magnetic field, then it will experience restoring torque. At mean position, its kinetic energy will become maximum and it will rotate further. Once again, in this situation, what will happen? This magnetic field will exert some restoring torque on it, and again it will rotate in upward direction. When it reaches at mean position, then what will happen? It will achieve maximum kinetic energy and further it will rotate in upward direction. If there is no loss of energy, then this needle will oscillate up to infinite time. Up to infinite time. If there is no loss of energy. याद हो तो ये चीज़ हम सिंपल हार्मोनिक मोशन में पढ़ चुके. x is equal to 0, then x is equal to plus a, x is equal to minus a. At x is equal to 0, velocity, that is maximum. Here velocity becomes 0 when particle oscillate like this. Here velocity will be maximum when it reaches to its maximum position, then its velocity will become 0. Again it will move in this direction. When it reaches at the mean position, its velocity becomes maximum, therefore further it will move in this direction. When it reaches to maximum position, its velocity becomes 0. Again it will move in this direction. This thing already we have studied in standard 11. जब सिंपल हार्मोनिक मोशन पढ़े थे तब ये चीज़ मैंने सिखाई थी. Now if you consider the example like this, in some bowl, in one bowl, if this type of marble is kept, then what will happen? If I displace this marble from its mean position, then this marble will move in this direction. Suppose I am giving some force to it in this direction. Due to that force, this marble will move in this direction. But when it reaches to some maximum point, then what will happen? Its velocity will become 0. It will stop, and further, due to force in this direction, marble will move in this direction. Will the marble stop here? No, it will move further in this direction. At some point its velocity will become 0. Again it will move in this direction. If we neglect the friction, then this marble will move up to infinite time. But if there is some loss of energy, then after some time this marble will come to rest. Same thing will happen here. If there is no loss of energy, then this needle will oscillate up to infinite time, and time period for its oscillation will be 2 pi under root I by mb. This is the formula of time period of the oscillation of magnetic needle kept in uniform magnetic field. क्या समझ में आ गया? एकदम परफेक्ट, बढ़िया. Next topic, that is dipole analogy. There is analogy between electric dipole and magnetic dipole. Electric dipole. And magnetic dipole. One upon epsilon naught is analogous to mu naught. It means reciprocal of permittivity of free space is analogous to permeability of free space. Second, for electric dipole moment is denoted by p vector. For magnetic dipole moment is denoted by m vector. Third, that is for short dipole, formula of electric field on the axis of dipole is equal to 1 upon 4 pi epsilon naught into 2p vector upon r cube. For short dipole, what does it mean? If we consider this type of dipole, minus q plus q, and distance between these two charges, that is 2a. Suppose I want to find electric field at point P from this center of dipole, then this distance, that is r, and if r is much greater than a, then this dipole can be treated as short dipole. शॉर्ट डायपोल लिखा हुआ है उसका मतलब है कि डिस्टेंस बिटवीन टू पोल्स इज वेरी स्मॉल इन कंपेरिजन टू पॉइंट ऑफ कंसिडरेशन एट विच वी वांट टू फाइंड फील्ड from the center of dipole. It means distance between center of dipole and point of consideration is very large in comparison to distance between either charge from the center of dipole. So this is the formula of electric field on the axis of electric dipole. EA vector is equal to 1 upon 4 pi epsilon naught 2p vector upon r cube. Same way, if I consider short magnetic dipole, for short dipole magnetic field on the axis is 1 upon 4 pi as it is. Instead of 1 upon epsilon naught, what should I write? Mu naught upon 4 pi into, instead of 2p vector, what should I write? 2m vector upon r cube. And this formula already we have obtained in chapter number 4. Magnetic field on the axis of circular current carrying wire, and circular current carrying wire behave as magnetic dipole. When we consider this type of dipole, this is south pole, this is north pole, and suppose I want to find magnetic field at point P, and point P is at a distance r from the center of dipole. If r is much greater than L, then this magnetic dipole can be considered as short magnetic dipole. Same way, if I want to obtain formula of electric field on the equator of electric dipole, for short dipole only, if I want to find electric field at some point Q, then the formula is 1 upon 4 pi epsilon naught into minus p vector upon r cube. Same way, here magnetic field on the equator of dipole is mu naught upon 4 pi into minus m vector upon r cube. This is the formula of magnetic field on the equator of dipole for short dipole. Fourth, torque acting on electric dipole placed in uniform external electric field, that is torque tau vector is equal to p vector cross e vector. For magnetic dipole, torque tau vector is equal to m vector cross b vector, because magnetic moment is analogous to electric dipole moment, magnetic field is analogous to electric field. Fifth, formula of electrostatic potential energy, that is UE is equal to minus p vector dot e vector. Same way, magnetostatic potential energy UB is equal to minus m vector dot b vector. UB is equal to minus m vector dot b vector. Sixth, formula of time period for the oscillation of electric dipole placed in uniform electric field, that is 2 pi under root I by PE. Same way, time period for the oscillation of magnetic dipole placed in uniform magnetic field, that is 2 pi under root I by MB, where I that is moment of inertia, P that is electric dipole moment, E that is electric field, M that is magnetic dipole moment, B that is magnetic field. So this is the analogy between electric dipole and magnetic dipole. ये सारी चीज़ें हमें कहाँ पे काम आने वाली है? When we will solve example and numericals related to short dipole, related to magnetic dipole, at that time these formulas will be very helpful to us. तो ये सारी चीज़ें हमें एग्जाम्पल, न्यूमेरिकल और MCQ में काम आने वाली हैं. So today we have obtained the formula of potential energy of magnetic dipole placed in uniform magnetic field. Then we have obtained the formula of time period for the oscillation of magnetic needle placed in uniform magnetic field. And after that we have studied analogy between electric dipole and magnetic dipole. I hope ये सारी चीज़ें आप लोगों को समझ में आ गई होंगी. आज हमने थियरी पढ़ी है. नेक्स्ट टाइम से हम कुछ एग्जाम्पल और न्यूमेरिकल सॉल्व करेंगे. आई एम स्टॉपिंग हियर. मिलते हैं नेक्स्ट लेक्चर में. तब तक के लिए बाय बाय. थैंक यू.